VLSos here. This is a video lesson on calculus in the context of trajectory, the path of an object as it flies through the air. We could imagine a ball being thrown, flying through the air, its position goes up, and then due to gravity comes down, maybe to the earth. We could be given the height of a ball that's thrown as a function of time. But we have to be careful. This graph here looks like the position of a ball may be thrown downfield as it goes up and then comes down. But this function is a height as a function of time. And if this graph were a graph of the h function, then time would be the horizontal axis and typically height the vertical axis. And this parabola is no longer the path of a ball, but just a graph of the height as a function of time, which is also a parabola. But we can't be confused. Time is not a spatial dimension. We're not watching a ball go downfield as it rises and falls. We're only tracking the height as time passes with an equation like this. We know that if we take the derivative of the height equation, then we get the rate of change of height. We could call that velocity. And this would then be the velocity of the object moving through the air. And if we take the second derivative of height, that'll be the same as the first derivative of velocity or the acceleration function. A is a function of time. An acceleration in these problems can be anything, but if the problem has to do with an object in the Earth's atmosphere, then it's gravity that's acting as the acceleration. And typically we give the acceleration the constant g. G is acceleration due to gravity, and it's constant, but it can be measured differently. It could be measured in feet per second, or meters per second. So we have to be careful that the constant g is, when we use it and evaluate, is the correct units. Negative 32 feet per second squared, or another typical gravitational constant is the one for meters per second squared, negative 9.8. Now, if we start with acceleration, we could integrate our gravitational constant and create the velocity function, which is going to be gravitational constant times time plus some initial velocity that we give the symbol v with the subscripted 0, and we call that v naught, naught for 0. The velocity function could be integrated again to get the position function. Integrating g of t, we get the gravitational constant divided by 2 times t squared plus v naught times t, and then the constant of integration that gets created then becomes the initial height of, in this case, maybe a ball. In our graph, the initial height might be the amount of height at the starting time, when time is equal to 0. And the ball is going to reach a maximum often, and it will come back down to have an x-intercept at some time as well. For example, what if we threw a ball with an initial velocity that we call v naught of 40 feet per second? And the initial height of the ball that we threw it at, as if it was coming off of somebody's arm, would be 6 feet. We could calculate the time at which the ball reached its maximum height. So we have a height equation in this situation, which is going to be g over 2, but the value of g that we're using here has got to be the one that matches the units given in the problem so far, So g is going to be negative 32 feet per second per second. Putting these values into the height equation, we have negative 32 over 2 t squared plus the initial velocity of 40 times t plus the initial height. This is the equation not for the trajectory of the ball, not for the complete two-dimensional path, but just to track the position of the height of the ball as a function of time. We're looking for the maximum, or when the ball reaches its maximum, we're looking for a t value. We are going to find that by setting the derivative equal to 0. A maximum will reach its height when the derivative is positive, becomes 0, and then is negative afterwards. So if I take the derivative of the height equation, it will be the velocity equation. In this case, I bring down the 2 in front and multiply by the denominator of 2 to cancel out, leaving the 32t plus 40, and the plus 6 goes away in the derivative. This velocity equation, I'm going to set equal to 0. Now think about the context in the real world of what it means to set a velocity equal to 0. Velocity is the derivative of height. So in a first derivative test, where height's derivative is 0, I might be able to justify a maximum. But if this is also velocity, it's the moment at which the velocity of the ball becomes 0 and is not moving. Now, if we can visualize a baseball being thrown up in the air, it's going to go up and move up until it slows down, and for an instant it will stop and have a velocity of 0 at its maximum height before it starts falling down. So conceptually, setting velocity equal to 0 will find the height of this ball. I can solve for t by subtracting 40 and dividing by negative 32. The negatives will cancel out, leaving t 40 over 32, or 1 1/4, 1.25. This is a critical point. It's a point at which it's a point in time at which the velocity is 0, and it could be an extrema of the height function. But to justify that it is a maximum, I still need the calculus making a sign line for velocity, putting the critical point as a tick mark, and finding the sign of the derivative before and after this proposed extrema. The sign of the derivative before 1.25 means I'll put 1 into the velocity equation. When I do, I get negative 32 plus 40. Positive term is greater, so I know that the derivative or the velocity is positive before 1.25. If I put a number after 1.25, this critical point, like 2 into the velocity equation, I get negative 64 plus 40 is still negative. In this case, because the derivative was positive or increasing before reaching the critical point and decreasing after, this has been justified to be a max. We have a maximum at 1.25. So we can answer the question, the ball reaches a max height at t is equal to 1.25 seconds. Don't forget the units when answering questions like this. And notice the difference between what the maximum height of the ball is and when the ball reached the maximum height.